So far the simulation looks promising, but it's missing something very important. The constraints will give the simulation much more realism, and they will let you make parts of the building more fragile or more resistant depending on what you want. For example, we could create relatively weak constraints within the wood parts and probably stronger constraints for the concrete. We could also art direct which parts of the building we want to break first or we want to break in a special way. So let's take a look into how we can create these constraints. And I will look here where we have the assemble node. And on a new branch, I will create a connect adjacent pieces. And I will connect this to the assemble. So what the connect adjacent pieces will do is find a name attribute and create a primitive between each one of the pieces it finds. Now take a look how we don't have many of these pieces. The reason being is that this initial search radius is very low. So let's increase this to say 3 meters. And now we have much more connections being created. Now another important parameter is the max connections. By default, only one connection will be created between each one of the pieces. So what I usually like to do is increment the connections so we have at least 2 or 3 connections. In this case, I will try with 4 and take it from there. So usually with RBD simulations, we're going to do a lot of testing and a lot of trial and error. But in the initial tests I did, 4 connections was working fine. You may notice that not only the concrete pieces are connected, but also the wood pieces are being connected to the concrete. And to make this easier to see, I'm going to create a color node and change the color only for the wood connections. So to do this, you can type @name equals wood asterisk. So now this color will be applied to every piece that starts with the name wood. So let's change the color, say, to blue. And we also need to make sure that the group type is set to points. So here we can see the connections that are being created for the wood beams. Now that the actual connections have been created, we need to add 2 primitive attributes that the constraint network will be expecting. So let's lay down an attribute wrangler. I will connect it before the color node. Change its name to set constraint attributes. And I will also change the color for the node. And make sure it runs over primitives. So the attributes we need to create are called constraint type and constraint name. Both of them are strings. So let's do this. Type s at constraint name equals open quotes, and the name can be whatever you want. I usually call it glue. So now you can close quotes and type semicolon. The second attribute is also a string, so type s at constraint underscore type equals open quotes and type all. Then you can close quotes, type semicolon, and control enter to evaluate. So basically that's all we need. Let's create a null just below the color node. Let's change its color to black. And let's call it out constraints. So now we can dive into our DOP network. And we will add a node called constraint network. And this node can be connected anywhere on the data tree. What I usually do is just connect it here before the output node. And it will expect at least one connection, which is the constraint relationship. And if you take a look here at the second input, it will indicate required constraints to create. So now I will add a glue constraint relationship. Make sure to connect it on the second input of the constraint network. And the first thing you'll want to do is change the data name to the constraint name that we created earlier. So for now, type glue, and I will show you where this attribute was created. And if you remember, here in this attribute wrangler, we created this glue constraint name. So back inside the DOP network, just make sure this is the proper name. So let's check and see if everything is working. So press play. So apparently we're missing something. Let's try to check and see what's happening. Okay, so one very important thing I missed. Back here on the constraint network, we need to specify where are the constraints or the subpath where we will find those constraints. So one thing we could do is go up one level, copy this null, go back to the DOP network, and paste here on the subpath with Ctrl V. Then press enter. And now everything is working, and we know that because here we see in red the constraints have been created. So let's go to our camera view and let's press play. So now notice how the building is holding up. It won't fall anymore. And this is due to the constraints. So the question now would be, how are we going to make the building collapse? And there's many different ways that we can do this. One of the most straightforward way to bring this building down would be to actually delete the connections that we have created. And let me show you what I mean. I will jump back up one level, and here after my color node, I will create a delete node. I will connect it, and under its properties, I will click bounding volume. I will click enable, and the default is bounding box, which is fine. So I will change the X size to 26, the C size to 26, and the Y to 4 meters. I will also bring the bounding box 1 meter above Y. So now if we take a look at the constraints, all the lower level constraints have been removed. And let me try deleting a bit more. Let's increase the size of the bounding box to 6 meters. And let's now go back to my DOP network. And here you'll notice how the red constraints, the guides, are not being shown. And that's because we don't have constraints here anymore. So let's press play. So now the bottom part of the building will immediately break, and the remaining constraints will also break if there's enough force exerted over them. Okay, so notice how some of the constraints never broke, and for this we need to work with a constraint strength that's here under the glue constraint relationship. So let's talk about this next. So as you may expect, the higher the strength value, the stronger the constraints will be. So let's try lowering this value, and let's again play the animation to see the difference. So notice how now most of the constraints are starting to break. Even constraints that are way up here are now broken. And this will give a more fragile result or a more fragile look to the concrete.